Your application is crashing, but not because of a bug. It is silently running out of memory. A memory leak occurs when an object is held by a strong reference after its life cycle has ended, preventing garbage collection. The most frequent Android leak involves the activity context itself. Configuration changes, such as screen rotation, trigger activity.on destroy, but if a background thread, a static field, or a long-running task holds a reference to the old activity instance, that instance cannot be collected. This retained object consumes memory until the application process is terminated. The retained activity often holds references to large resources like views and bitmaps, rapidly exhausting the heap. Identifying the specific strong reference path is mandatory for remediation. LeakCanary must be integrated exclusively into the debug build type. Add the dependency com.square up.leakcanary:leakcanary-android using debug implementation in the module level build.gradle file. LeakCanary 3.0 utilizes the App Watcher library for automatic setup. No manual initialization code is required in the application class. The library automatically hooks into the Android lifecycle to track instances of activity, fragment, and view model. This automatic tracking ensures that objects expected to be garbage collected are monitored immediately upon destruction. This setup minimizes performance overhead in production environments while maximizing leak detection during development. LeakCanary uses an object watcher to monitor objects that have been destroyed but are still strongly referenced. When an object is tracked, LeakCanary waits for a short delay and then forces a garbage collection cycle. If the object remains strongly reachable after 2 consecutive garbage collection cycles, LeakCanary determines a potential leak exists. This triggers the creation of a heap dump, which is a binary file with the .hprof extension containing a snapshot of all objects and their references in the Java virtual machine heap. Heap dumping is a blocking operation, which is why LeakCanary is restricted to debug builds. The object watcher mechanism ensures that only genuinely retained objects initiate the expensive dumping process. The core output of LeakCanary is the leak trace, which identifies the shortest strong reference path from a garbage collection route, or GC route, to the leaked object. A GC route is an object that the garbage collector considers reachable, such as a static field, a running thread, or a local variable on the stack. The trace lists the sequence of objects and fields that maintain the strong reference chain. The developer must analyze the field immediately preceding the leaked object in the trace. This specific field represents the reference that must be broken or nulled to fix the memory leak permanently. Storing an activity or view context in a static field creates a permanent strong reference, preventing the context and its associated resources from being collected for the entire application lifetime. If a context is required for a static utility, use the application context instead, which is tied to the application process lifecycle, not the shorter activity lifecycle. The application context prevents activity retention. If the static field must temporarily hold an activity reference, ensure the reference is explicitly set to null within the activities-on-destroy method. Nulling the reference immediately breaks the strong chain upon destruction, allowing the garbage collector to reclaim the activity instance. Non-static inner classes, including anonymous classes like runnable or handler implementations, implicitly hold a strong reference to their enclosing outer class, typically an activity. If an instance of this inner class outlives the activity leaks. Common examples include delayed messages posted to a handler or background tasks like the deprecated async task. The solution requires declaring the inner class as static. Making the inner class static removes the implicit strong reference to the outer activity. If the static inner class needs access to the activity, pass a weak reference to the activity instance instead of a direct strong reference. The weak reference allows the garbage collector to collect the activity, even if the inner class instance persists. LeakCanary allows manual tracking of specific objects using app.watcher.object.watcher.watch, passing the object and a description. This is necessary for custom objects that are not automatically tracked by the framework integration, such as custom singletons or specific service instances. Framework bugs or known intentional leaks in third-party libraries can generate false positives. Use excluded refs configuration to instruct LeakCanary to ignore specific fields or classes during trace analysis. Exclusion rules prevent noise and focus the developer on actionable leaks. Exclusion rules are defined using the fully qualified class and field names within the LeakCanary configuration block. After implementing a fix, repeat the exact scenario that previously caused the leak to verify successful remediation. LeakCanary should no longer report the specific leak trace, confirming the strong reference chain is broken. Due to the significant performance impact of heap dumping, LeakCanary must be strictly excluded from release builds. Ensure the debug implementation dependency scope is correctly applied in the Gradle file. For deployment, verify that the release Android package kit does not contain the LeakCanary library code, maintaining optimal application performance and minimizing binary size.